temperature effects. So we saw already that the temperature of the oil affects the viscosity fairly strongly, in fact. So typically, a typical range that we want to be using is, around the 71 degrees Celsius range. For again, that's kind of like a value that is reasonable for kind of some of the more typical oils that you might be using for your lubrication. If it gets too hot, if we start getting up into the 90 degree to 120 degree range, you do have a tendency for lubricants to start breaking down. Now, that having been said, both of these values are very highly dependent upon exactly what oil you're going to be using. So again, check what the manufacturer is saying. So they're going to give you the guidelines upon what a usable range is, and you should be able to look. And they should be able to give you kind of its a viscosity profile. So yeah. So anyway, the main assumption here is that all of this heat that's being generated is generated in the oil, so it all goes into heating up the oil. Like it's all generated by the viscous shear that is going on within the oil. And a general idea of how much heat it will take, it's volumetric heat capacity for kind of normal operating range, 1.36 megapascals per degree Celsius, or 110 pounds per inch squared degree Fahrenheit. It's reasonable. So you got that. You got a certain amount of oil. So if you got your bearing in operation, you're going to be losing some oil out the side. And do the side flow, which we just saw how to calculate, and some of it's going to get recirculated. So essentially, you're going to get kind of we're going to be kind of when we kind of try to figure out what the viscosity of our oil is, we kind of got to pick a temperature to use. So what we like to use is the average temperature. So you're going to get kind of an inlet temperature and an outlet, an inlet temperature and the an inlet temperature and outlet temperature. So you're going to get a certain amount of heat that gets pumped into the oil as it goes through, and then it's going to get its way back around, and it's going to mix with the oil that so the oil that gets recirculated is going to mix with the oil from the inlet, and you're working off the average temperature of the oil that is in the hydrodynamic wedge. So basically, you take the two oils that are coming in, the inlet and the recirculated stuff, find out what their temperature is once you're mixing based upon what portion gets recirculated, and then figure out what the outlet temperature is based upon how much heat is generated, and then that'll allow you to get an estimate of what your viscosity, what temperature you should be working at, and your viscosity. Now this is going to a degree going to be an iterative process, because you can't necessarily calculate how much heat you're pumping into it until you know the viscosity, and you can't know what the viscosity is until you know how much heat you're pumping into it. So yeah, a bit of an iterative process. So for self-contained bearings, we don't have recirculation we're not feeding it oil at a particular temperature that we've had a chance to cool. That's the good thing about the other non-self-contained bearings, is that we were able to actively cool the lubrication oil. Of course, doing so is takes effort. It takes it increases your equipment and operating costs, but so be it. But for self-contained bearings, so the oil that leaks at the side is recaptured, recirculated internally, and then basically all the heat that's generated needs to go somewhere, and the oil itself isn't carrying it off to some heat exchanger or what have you. So you're relying only upon convection to get stuff out of there. So we just look here, basically the rate of heat dissipation that we can expect, this H, it's in watts, is going to be equal to a heat transfer coefficient, watts per hour per square meter per degree centigrade, times the exposed housing surface area. So what is the surface area of that bearing, and then the times the temperature difference. So the difference between the average oil film temperature and the air temperature in the vicinity of the housing. So if we solve for T naught to figure out what our average oil film temperature is, that's going to be that TA, the ambient temperature, plus the H over Ca. So some estimates for what that coefficient is based upon what type of bearing you have, in particular, like what type of oil circulation type you have, as well as the conditions in the area for airflow. So if you have an oil ring or collar type, you're using the top row. If you have an oil bath type, you're using the bottom row. And the if you're in still air, so if it's like an enclosed space, perhaps, then you're using this column. If it's average air circulation, you're using the middle column. And if you're actively pumping air such that it's moving at an average of 500 feet per minute, then we can be expecting to get this one here. So that is what we can use to estimate our heat generation or our heat loss, and kind of narrow down what our temperature is expected to get in those bearings. So just in general, when we're talking what's going on here, so we'll have a few direct variables. Unit load is the most obvious one, and speed. Viscosity. Viscosity can be it's a direct variable and an indirect variable because it depends a lot upon temperature raise, but we can target it by changing what oil we use. So it's a direct indirect variable to a degree. Now, obviously, the bearing dimensions are stuff that we can change as well. Indirect variables: coefficient of friction, temperature raise, volumetric flow rate of the oil, both side, total and side flow, and then the minimum film thickness is the stuff that we need to try to control using those other variables. So in current practice, we have certain kind of let me try. There we go. certain kind of maximum load capacities that we tend to use based upon what the type of load is. So if we have a fairly steady load, an electric motor, steam turbine, gear reducers, centrifugal pumps, then we can kind of justify using load capacities like this. If we're going for the more fluctuating loads, then we basically are going to have to use bearings that have load capacities in higher ranges. So like the diesel engines will have their main bearings or connecting rod bearings could be in the 6 to 12 MPa range. If we're talking gasoline engines, main bearings are going to be a bit lower. Connecting rod bearings will be a bit higher. But that's kind of what a good guideline for kind of picking what bearing you're going to be using, or sorry, picking what. Well, essentially, this will be used to pick what bearing you're going to be using, because it'll be used to select your L/D ratio, because you're going to know what your maximum load is. So what we're going to be wanting is we're going to be wanting to ensure that when we're in operation, we have a particular H0. So we want to, when we got our rotation going on, got our wedge forming, we're worried about the size of that gap there, right? We want it to be sufficiently large so that it, any debris that might come off is able to clear it, as opposed to getting squeezed in there and then gouging into your shaft and your sleeve, and so on and so forth. So we're trying to prevent metal on metal contact. So we're going to be calculating this, and basically, if we want to apply a particular we want to be calculating this and applying a certain safety factor. So if we calculate what the H0 would be based upon twice the load that we're twice the load that's actually in operations, then we could say that that is suitable. Again, if it's above kind of this reasonable threshold, then we're going to say that's suitable. So of course, obviously, your safety factor might be mandated by some regulation, or it might be mandated by the client or what have you. But that kind of allows for a bit of overload to occur and still allow us to ensure that we're operating safely. So clearance ratios are going to be, what's available is variable and depending upon how much you want to spend. So the thing to keep in mind is that anytime you're buying these things, you're going to get a certain tolerance range. So the size of your journal and the size of your sleeve are, they're not going to be exact, because you can never manufacture something that is exactly the size you need it. You can have a certain tolerance range. So you need to ensure that for your design, when you have any particular when you're doing your design, you do need to ensure that it works and that it's safe for all of the tolerance ranges, for all the clearance ratios that could arise as a result of those tolerance ranges that you're working with. So that needs to be kept in mind too. So yeah, we want to ensure that our H naught is going to be large enough to get that full thick film lubrication. We don't want the intermittent contact going on. We want, generally speaking, obviously, we want our friction to be low as possible. So again, we're kind of staying in that optimal zone. Need to make sure that you're supplying enough cooled and cleaned oil. Need to make sure that the oil doesn't heat up too much. And again, the actual allowable temperature depends greatly upon what actual oil you're using. You want to ensure that the oil gets distributed over the full length of the bearing. So oftentimes this is going to be involving you cutting grooves into the sleeve, and then the oil is supplied to those grooves. Now again, do not put the grooves in the loaded areas, because having a groove in the loaded area will greatly decrease the load carrying capacity of your bearing and may inadvertently result in a lot of metal on metal contact and grinding, and things go bad. So if you know that your groove, if you know that your load is going to be pointing in a particular direction, then put your oil supply groove in on the opposite side. And of course, if there's kind of a range of directionalities that the groove might, that the oil might be, the load might be pointed, then you need to adjust accordingly. The bearing material itself, again, needs to be strong enough, but embeddable. Again, that's when we have little bits of debris that arise, we want to be able to have them kind of drive into the materials. That's why we tend to use Babbitt. So embeddable, conformable, corrosion resistant is important. We don't want this thing to be rusting over time. And yeah, generally speaking, we want to be minimizing shaft misalignment and deflection. The analysis that we did was kind of based upon the idea that the shaft is going to be concentric. So that our journal is going to be concentric with the sleeve it's inserted into. If you do get misalignment, then it can cause issues. You're going to get kind of different. You're going to get a weird pressure profile. You're going to get different. So you're going to be introducing. You're going to get higher pressure on one side, lower pressure on the other side. So you're going to be basically introducing a net moment to a degree. Yeah, not ideal. Load during startup should be low, or startup time should be low, preferably both. So again, when we are starting it up, when it first starts up, that journal is sitting at the bottom of the sleeve, so it's always going to be, you're going to get at least some degree of metal contact when you're starting up. So if you start up with a low load and then increase once you get up to speed, then that significantly decreases the amount of wear that'll occur during startup. Whereas if you start from a dead stop and get up to speed really fast, then again you're minimizing the amount of metal on metal contact, because it just does, the wedge forms fast. But generally speaking, if you can arrange it to have your startup load a lot smaller, then that may be ideal. If you can't, and if you're starting and stopping a lot, and it's a situation where you what am I trying to say? And if it's a situation where you can't, yeah, if you're starting and stopping a lot and your startup load needs to be high, then you may want to investigate other options. So for example, trains used to use hydrodynamic bearings for their wheels. They don't anymore, because at the beginning, the startup sequence would basically have enough friction that they needed to have like double the engines uh, in order to drive your train uh, to get going, and then essentially once they got going, they'd have one that was uh, redundant. So they moved to roller bearings for those as a result, because roller bearings don't have that higher load, so that higher friction at startup, and again also they don't have the concept of the higher wear at startup as well. And then again, various ambient operating conditions. So if you can highly control the temperature range that will be seen in in and around your bearing, then that could be fine. If not, you need to kind of do your analysis based upon a varying range. And yeah, sometimes your users won't follow the exact recommendations on the oil. It can be helpful to ensure that that's not going to be catastrophic. And oh yeah, if the load vector rotates. So again, the analysis that we've been done, basically we're pushing down on this bearing and we're just pushing down upon it and then rotating. If the load rotates around as well, then that will affect the apparent rotational speed. Also, if the load doesn't fluctuate and the shaft fluctuates, but the bearing also rotates, then that affects the apparent rotational speed. So keep that in mind if you, in the future, if you have any situations that kind of follow that. So you'll need to adjust your parent in. We're not I don't think we're going to be doing any problems that will have that for this course, but in the future that might come up. So you'll need to remember that you need to take that into account. All right, and we'll do a few examples.